In the previous class, we have shown the T matrix is I interaction Lagrangian. That is actually action, I action. That interaction Lagrangian integrate over space and time. And because it is too complicated to keep all the speed of light in h bar, from now on we just put c and h bar is equal to 1. Recall that the Lagrangian for the electromagnetic interaction is minus 1/4 f mu nu f mu nu, and there's an interaction term minus j mu a mu. When we derive the equation of motion for this Lagrangian with respect to a mu, we just took the derivative for, what was the equation? Something like so the field was a mu, right? So equation of motion for this was like that, right? So just let us copy this result to find some change in the equation of motion for the charged particle Lagrangian. If we first write down the free particle Lagrangian for the charged scalar particle, we have derived this expression. And here phi and phi star are independent field, right? Because we had introduced the two real scalar field to express the complex scalar field. So phi 1 and phi 2 are independent. So in the same sense, phi and phi star are independent. The equation of motion for phi can be obtained by imposing the variation principle for the phi star. And if I take the derivative for the phi star, the final result for the equation of motion phi is obtained. That is Klein-Gordon equation. So in that case, the modification of the Lagrangian for the phi star field can be made by multiplying minus j some current. Because phi do not have any vector index, let us just assume that j is a scalar. Okay? Remember that in the previous derivation for the charged scalar field by making use of gauge covariant derivative, this j was proportional to the derivative of phi multiplied by a mu, so that it becomes a Lorentz scalar. Remember, right? Momentum of the scalar field multiplied by the gauge field, right? So this j is actually proportional to a mu and also proportional to round mu phi. But that is all included in here, because today we would like to see the whole structure, not in detail. Okay, so replacement of the current interaction potential can be made by minus j multiplied by phi star, and j is a Lorentz scalar. So if we add these term in here, the kinetic term doesn't change, only this partial derivative changes. That effect is additional j. Okay? And if I move this term to the right hand side, in comparison with the homogeneous equation that is for the free particle case, additional piece appears in the non-homogeneous equation. Okay, if we want to solve that kind of the non-homogeneous partial differential equation, it's better to understand the answer for the case where the right hand side is delta function. Okay? If I know the answer for this non-homogeneous equation, then we can integrate arbitrary function and integrate over that variable so that we can change this delta function into arbitrary function. So it is good to know the answer for this non-homogeneous equation. So this is usually when we learn the electromagnetism, we learn that as a Green's function. And in the case of particle physics, we call this as a Feynman propagator. Okay, let us assume we have found the answer for this, and let's see what happens if it is the case. The answer for the original equation is like that. Let's see why. Just substitute this result into this non-homogeneous equation. Then we have Feynman propagator and the current Jy. Note that this is independent of x. We have x minus y here and y here. So this derivative is with respect to the variable x instead of y. If I act this operator to the wave function phi, it passes through all the way to here. And this derivative does not act on the variable y. So we make use of this fact. This is delta, the same number, and the x minus y is in here. Minus delta, x minus y. If I integrate over y, all four variables, the 0, 1, 2, 3 components of the variable is replaced with x. So that the right hand side is minus jx. So we have shown that this is the solution for this non-homogeneous equation. So next class we will learn how to derive this Feynman propagator. But here we note that if I know the Feynman propagator, then I can compute the T matrix that has the interaction, right? So T matrix was written like that. Integrate over the four-dimensional space of the interaction Lagrangian. And interaction Lagrangian in here is a J phi that are both a function of x. But let us make use of the fact that phi x is minus j of x. So if I phi x minus j of x, but let us make use of this. Where is it? Is this? Phi star. Right. Phi is like that here. This guy is substituted in here. Then this j of x is the same, minus I is the same. I have additional integral over y, and this is delta f star x minus y, and phi is this one, so I have a j star y. Let us put this negative I in either one of the current vector, and then just keeping the algebra vector 1, I put just I and minus I. Then each current has minus I vector and Feynman propagator as I vector. In the next class, we will derive the explicit expression for the Feynman propagator.